So really today I'm going to talk about unsupervised, a fundamental technique actually which could enable how cars can share data and interpret each other's data. Okay, and that's very fundamental to achieve and perceive environments, right? So now before I go into it, right, I just want to get how this started, right? The story of this is very, I have told this once last before, right? I was at Toyota, at least in Bay Area, and was hanging out with one of my friends, and he was like, dude, you got to learn computer vision. This is so much cool stuff happening, right? Everybody's doing it, right? We spent 1 month doing a lot of deep learning algorithm building. So here's the problem, right? Here's how cars work, right? They perceive environment, they localize themselves, get the maps, right? And use their sensors to perceive things and then plan their path and then it's sent to the controller, right? That's the highest level so that everybody is on the same page with me, right? And what really I believe and what the vision which has been proposed before as well, right? This is what really we want to go to, right? The local sensors guide this right now, but we want to go to a world where V2V or V2X data can guide all these things, right? Cooperative perception, cooperative mapping, localization, right? So we are doing all these things, right? And here are some of the top challenges you want to handle, right? Okay, for mapping, localization, perception, path planning, right? Very much, I'm going to focus today on non-line of sight perception, okay? So yeah, sure, I will give you a little bit of a high-level overview of all the things which can be possible with the cooperative perception, right? But the slides will be available for you to review, right? But this is something which by the way, I just want to acknowledge the collaborator who helped create some of these slides with me, right? So he's the one who has a great knack for these things, right? Gaurav, right? And just want to also acknowledge some of the students, just that I realized that other students were giving talk. A lot of students are working on this project, right? Two of them who contributed most to is right now Yu Meng and Indrajot Singh. Probably he's in the audience. I don't see him yet. Maybe he was working till last night till 4 a.m. on the slide, so he may not be here. So, all right, let's get to the part of automated driving, right? We see all of the automated driving, and they barely are safe, right? And if you go to DMV's record right now, they are more unsafe than human drivers, right? For the number of miles they have driven, right? If you average across that. And very interestingly, DMV has a very detailed report for every accident they cause, okay? So you can go read every detailed reports, right? And one of the major reasons why these cars are failing is because of perception, okay? You can't perceive all these accidents are cause of limited perception, right? There is a pedestrian which is not being able to perceive because of something else blocking the view, right? And when that pedestrian, this car wouldn't see for a few more seconds, this pedestrian is going to get killed by this or maybe get obstructed by it, okay? So what collaborative perception or cooperative perception can enhance is that you can identify this person by using the sensors of this bus, right? Okay, that's basically the highest level everybody wants to achieve, right? Now, one of the biggest challenges in doing this cooperative perception, and why now, as you can see, DSRC, a lot of people are already deploying, right? At least I know for sure DSRC is getting deployed in Japan extensively, right? Not only that, now the purpose is one of the problems with the cooperative perception is it's really hard problem, okay? For standard task like, okay, if I have a sensor, right, I can measure some kind of a ground truth, right, and understand that behavior better, right? However, for cooperative stuff, there is no way to even label and understand, right? Because it's relative to two cars. How do you label things when they are relative to two cars, right? So there is no data set exists right now. And this is where the front, if you look into what Sujit and the team is doing here really, is trying to enable this platform to collect data, right? Here I'm labeling all the top data set which have been collected by computer vision community, right? And none of them meet the bar for cooperative data collection, okay? And technically, I have a very complementary approach, right? Since there is no way to label, let's just go unsupervised learning, right? Let's just, maybe we'll use the labels for the context of testing them, okay? So last time when you all were here, right, we were in the phase one, right, where I presented how we can use monocular camera with combining time and space diversity to do depth and velocity and motion estimation, right? Now, today what I'm gonna focus is that what we realize is much more important, right, by talking to a lot of people in industry, even Qualcomm included, right, and understanding that one of the fundamental problems, right, is to translate the views, right? If I have a data from another car, right? How can I translate that to my point of view, right? So this is what we're going to focus. This was the phase one's result, right? Here's the phase two, right? So overall, the idea is following. You have these multiple cars, right? Each of them have their field of view. What you really want to do is you need to combine all their views, right? And the way to combine their views is that you will do a relative translation, right? You will translate everybody's images into your frame of view, right? And combine them. And this is called as relative camera pose estimation, or very popularly called as camera pose, relative camera pose, right? Just for the context of the rest of this talk, right, let's just say it's going to be relative camera pose, okay? And I'm going to give you an algorithm which does this really well, okay? So now, what is relative camera pose, right? For example, right, here is how it works, right? So you have car A and car B, okay? If you want to combine their data, right, okay, what you need to know is not just the translation between these two cars, right, but you also need to know the camera's orientation, how it's oriented. Only then you can combine the data and then you can understand this car can see this pedestrian and this car cannot see this pedestrian, and then they can combine their views and can enable this car to see something which is not visible here altogether, right? Now, now one natural question is, right, hey, why not just use GPS, right? Like GPS is always there, right? It can give you location, right? So the point I want to emphasize here is that some people who are new to this, like basically GPS doesn't provide you with orientation information, okay? It just provides you with the location, which is insufficient to do any of these combining view translations, right? And there are many other calibration techniques and so on and so forth, right? All these requires that the two cars have commonality in the scene, right? They use the commonality in the scene to do translation. For example, right, take car B and take this tractor here, right? If they both see the same scenes, they can associate with each other, combine their data, and based on that, they can translate. But the problem is that this car doesn't even see this blocked pedestrian, right? So the value addition of combining this car's data is almost insignificant or insufficient, not even useful, right? So really what you want to do is combine the car data from car A and car B, okay? And look at car A and car B's view. They are perfectly orthogonal to each other. They are looking at entirely different things, okay? And from entirely different perspective, right? Now, so relative camera pose, sorry, I keep wondering that if I'm gonna fall or not. But relative camera pose, right, is a well-studied technique. And the reason why they studied this technique was not for collaborative perception. They just wanted to put two cameras on the dashboard and combine their data, okay? And even in that case, slightest orientation mismatch can cause problem, okay? So this is where they studied extensively relative pose. And what they relied on was scene overlap. Whenever there is a scene overlap, I can combine data, right? And I can translate data. Now, here's what we're gonna do here. In the world of context of collaborative perception, that technique is not useful. Primarily because the cars whose data you want to combine won't have scene overlap with you, right? And the cars whose data you can combine has scene overlap but does not have a complementary information to you, right? So fundamentally, we reach to a point of conclusion, right? Look, scene-based techniques cannot be used, okay? You need to come up with something fundamentally new and think in different direction, right? And this is where our thought process is, right? Okay. So scene-based techniques will fail for minimal to no overlap, right? In order to maximize the information, right? So now to maximize the information, right, here's our key idea. Our key idea is that in this context, we'll take a look at this car C, which is, even though these two cars A and B have perpendicular or orthogonal overview, C can still see, or C is still visible from A and B. So what you will do is you will estimate geometry of C with respect to A and B, right? And use that commonality to figure out the orientation between A and B, and then use that to understand where this pedestrian is located, okay? That's the highest level message I want you to walk away with, right? Instead of doing scene conditioning, right, and scene overlap as a metric, we are gonna use co-visible object, right? And this is something very new concept which we have introduced, right? And this is under submission, and I presume The recordings may be delayed because of that, but to adhere with the double blind policy. So this is the overall pipeline. You have two cars, car A, car B, right? They do, I think I'm out of the time, but really I'm gonna just emphasize that basically we are using some of the work into detecting and associating the objects from the prior teams, right? So you can leverage detection and association of objects. Once you detect and associate, we augment the input with depth augmented maps, right? And then looking at the depth, we can figure out the geometry using the CMEs encoders, right? And that upon figuring out, we can get this really the pose, right, which is a seven-dimensional vector, which has 6 degrees of freedom and 1 for translation, right? Okay. So I have 2 minutes left. In 2 minutes, I'm just going to quickly maybe give you one other point, which is this is supervised architecture I showed you, right? And here's our unsupervised way of doing it now. So we extended this entire kernel of idea into an unsupervised idea using uResNet decoder. What basically it does is that it takes camera B and estimates depth of camera A and keeps on doing iteratively between each other and trying to figure out what is the right way, how to do it unsupervisedly, right? So really this basically makes, and this we basically then created this is a video of our, I hope it plays, but it's basically a simulator which we created this framework in where we collected a lot of data from multiple cars, right? The video is not playing as usual, but let's go to this point. There are some these images which are showing the actual data we collected, right? And it has a lot of low lighting condition, high lighting condition, bad weather, and so on and so forth. And here is what we see as the depth map after translation, right? To give you, so if you took the relative pose, right, you will get 60 meter of translation error, right? And if you take our best result, you will get 13 meter of error, right? And this is 13 meter in mean, but in median, I guess you can take it to 7 meter, right? And if you do X by M, which is the more important metric which all computer vision use, right? What it says is that per meter, how much error am I going to introduce, right? So what it says is that after doing this translation, we'll have 16 centimeter of error per meter, which is a tolerable range, okay? I just want you to walk away with that metric, and this is unsupervised learning model, right? Okay. And yeah, we thank Toyota ITC, and they have been extensively supporting our research. And we also thank CWC for providing their support to this research. Questions? I left with 2 minutes. 1 minute, I saved 1 minute. So you get 1 more minute for questions. Go ahead. Go ahead.
Yes, so for relative pose, are you still going to use GPS or, just...
Is GPS less? We can augment with GPS if we want to, but we just went all, let's just discard GPS for now.
You showed the intersection, like
yes.
Cars that can't see each other.
Yeah.
There's a building in between. How do you get the relative pose since neither car is in view of the other?
Yes, so
this would be
they work.
Yeah, B and C. How do you get the relative pose between B and C?
You don't need relative pose. You need just to see C from both A and B, right? And you combine A and B's data, right? So C is used as a common object between A and B. So you get common object C's depth with respect to A, you get its pose with respect to A, and you get its viewpoint, right? And then you do the same thing with the car B. You get the depth pose from car B, right? And then you look at this common object, right, is seen with this different distance, this angle, and same thing from the other, right? And if that's the case, right, what would be the geometric overlap for the other objects you have in this environment surrounding?
Okay, I guess what I was thinking of is C isn't quite as close to the intersection, so B can't see him.
Oh, I see. No. I think it can see, I guess.
But B doesn't see C yet.
In this contrived example, A can see C and B can see C.
Okay. Right.
So just to go ahead, yeah. One more question, I guess. Go for it. Yes, it can be mobile object. Yes, you're correct. So interestingly, I think, let me just give you more insights on that, right? I think so far our class of common objects is slightly limited to all these cars and trucks and these things. I think more importantly, it will be interesting to understand how buildings and other things can be used more for common poses, right? Common objects, right? Co-visible objects, right? And that is something we are exploring. And yeah, I think let's see how it works out. Yeah, yeah. Partly because we don't have labels of segmentation. It's fine. We can talk about this more offline.